Okay, good morning, everyone. Thank you so much for coming out to my talk today, and thank you so much to the organizers for organizing such a great conference and for inviting me to present. I wanted to just start by telling you a little bit about myself. I grew up in Winnipeg, and I moved to Waterloo about 6 years ago to do my graduate studies here. So I did both my master's and my PhD at the Perimeter Institute and at the University of Waterloo. And I had just defended my PhD about 3.5 months ago under the supervision of Roger Melko. And so what I'm going to be talking to you about today is some of the work that went into my PhD in one section of it. So specifically what I want to talk to you about is how we can use quantum entanglement to gain information about critical systems and phase transitions. I wanted to mention that quantum entanglement is a really exciting phenomenon, and there's lots of present and future applications and technology under investigation here at the Institute for Quantum Computing. But specifically what I want to talk to you about today is how we can use quantum entanglement to gain information about universal numbers. So I'm going to start by motivating why we should be interested in these universal numbers and what they can tell us about critical systems and phase transitions. Then I'm going to talk about how we can learn about some of these universal numbers from quantum entanglement and how we can extract them. And I'm going to give you some examples of some of these universal numbers that we've studied in 1 and 2 dimensions. Okay, so I wanted to start out by just talking a little bit about phase transitions. So in condensed matter physics, we're often interested in taking a model and studying the different types of order or phases it can have as we vary certain types of parameters, such as the temperature. And one thing we can examine when we do this is the correlations within the system. So if we're measuring some observable quantity, we would expect that if we're studying 2 regions of space that are very close to each other, that these observable quantities would be very correlated and they would have an influence on each other. But as they move further apart, we might expect them to be more independent. Specifically, if we study something like a correlation function, we often observe that it has an exponential decay as we increase the distance. And this parameter called the correlation length parameterizes this exponential decay in this case. So if things are decaying very quickly, then we have a very short correlation length. And if they take a long time to decay, then we have a longer correlation length. And one thing we can study is how this correlation length varies as we tune one of our parameters. So for example, as we change the temperature. And one interesting phenomenon is that if we're at a continuous phase transition, several quantities are going to diverge. So at the continuous phase transition, we call this a critical point. So this is my critical temperature in this case. And among other quantities, the correlation length is going to diverge in this system. So this means there's no longer a finite range that can be used to describe the correlations in the same way that we can at other temperatures. And so what we want to kind of come up with is a way of explaining this criticality, so a way of describing the physics exactly at these critical points. So one way that you may have seen before of doing this is by using something called critical exponents. So for example, in order to describe how these quantities diverge right within the vicinity of these critical points, if we want to study, for example, the correlation length, this diverges with a parameter called nu. So this is our critical exponent that governs the behavior of the correlation length in the vicinity of the critical point. And similarly for other quantities, such as a susceptibility, we use a parameter called gamma. And so these are parameters that allow us to describe the critical features of this model. And there's also other universal numbers that we can use in order to describe this. And so throughout this talk, we're going to kind of explore other universal numbers that we can use to describe this type of critical behavior. So now I'm going to talk a little bit more about universal numbers in a different kind of way. So on the left here, I'm plotting something called a renormalization group flow. So we can imagine I have some kind of a model that's parameterized by some set of parameters. Here they would be P1 and P2. And if I take my model and I try to do some kind of a renormalization or rescaling procedure on it, in some cases what I'm going to find is that if I do this renormalization procedure, I can end up with a similar model, but with some redefinition of my parameters. So in this way, I can observe some kind of a flow in parameter space as I do some kind of a transformation on my theory. And so the blue points here are fixed points associated with criticality of my model. And then the green lines show how I would flow between these. And so the reason that universal numbers are so interesting is because they divide systems into universality classes. So at these fixed points are going to be characterized by a set of universal numbers. And what's so cool about this is that I could imagine having two very different models that are extremely different from a microscopic perspective, and yet they might still be able to have the same set of universal numbers. So it might be that I start with some very complicated theory with with many degrees of freedom, but it turns out that the actual number of effective degrees of freedom needed to describe the system when I'm exactly at criticality is much smaller than the number of degrees of freedom that I start with. So this can give me some kind of insight into the symmetries and the simplifications possible in my model, and show me that there's actually some kind of connections between very different models that might appear to be not similar at all when they're critical. They can actually have a lot of similarities. So some of the goals that we have in studying this type of situation is that we'd like to really understand a little bit better how we can characterize some of these fixed points. So we'd like to explore a lot of different universal numbers at these points to try to better understand how we characterize these points and what it really means and what are the actual relevant degrees of freedom at these fixed points. We'd also like to understand the relationship between these points a little bit better. So for different universal numbers, how do these numbers change as we move from one fixed point to another? And specifically, what I want to explore in this talk are various types of universal numbers that we can extract from quantum entanglement. So now I want to talk to you a little bit about entanglement. So on the top left here, I'm just showing a picture that you might often see something like this when you first study entanglement, which is just two particles that are connected in some way. But more generally, when I'm studying entanglement, it doesn't have to just be between two particles. It can be between a many body system. So that's what I'm showing here. So I have some large region A, and then its complementary region A bar. This is what we're going to be studying in this case. So we can, in either of these cases, we can store the information about the state somehow in a reduced density matrix. So the information about the entanglement and the state that we're in is going to be within this matrix. And then in order to come up with a way of quantifying the entanglement, what we're going to use is something called the Renyi entanglement entropy, which is just given here. So this quantity is parameterized by this parameter alpha, and we also need to know this reduced density matrix in order to calculate it. For those of you who have calculated entanglement before, you might be more familiar with this formula down here. I'm just going to note that this Renyi entanglement entropy is just a more general way of studying entanglement entropies, and if I just set the alpha index to 1 and take the limit properly, I recover this more familiar formula. So we can just gain a little bit of extra information about our entanglement by using this more general formula. And so if we're in a case where A is not entangled at all with its complementary region, then this entanglement entropy will just be 0, and it increases as these regions become more and more entangled with each other. Okay, and so we want to try to extract some useful universal numbers by looking at these entanglement entropies for various types of setups. So various models, various types of region A's, various types of system sizes, things like that. And so one thing that I want to start by talking about is a property that's been well established, which is that for many quantum states, it's been shown that the ground state obeys something called an area law or a boundary law. And what that means is that if we're in the ground state of a system, the entanglement entropy is going to scale proportional to the size of the boundary that separates the regions. So if I just have a flat boundary like I have here, and the length of the boundary is just L, then my entanglement entropy is going to be to leading order, proportional in L. Similarly here, I could have a more complicated region, but the characteristic length scale or the perimeter of this area, if it's proportional to L, then I would expect my entanglement entropy to be proportional to L. So this type of area law scaling is something that's been seen for many systems, but we don't actually have an exact explanation of how it occurs. So what I want to talk about now is a model that we can use to recover this area law. And it ends up being very useful for making other predictions for other types of geometries as well. So I'm going to motivate this model a little bit, and then I'm going to show you how we can use it for other types of boundaries in order to extract universal numbers. But I'm going to start by talking about just a very simple flat boundary between regions. And for the model I'm going to introduce to you, I'm going to make a couple of assumptions. The first one is that when I'm measuring entanglement, I'm going to assume that it's most influenced by contributions that are local to the boundary. And the second thing that I'm going to do is motivated by studies of renormalization, I'm going to assume that we have to sum contributions to entanglement over length scales. So I'll show you what that means in the following slides. So it turns out that to do this argument, to use this model, we have to put our theory on a lattice so that we can have some minimum length scale of entanglement. So that's what I've done here. I've just taken this figure from this previous slide, and it's supposed to look the same, but just on a lattice now. So what this means is that I need to, as I said, introduce some kind of a minimum length scale that I'm calling A. So from my first assumption, I'm assuming that my most significant contributions to entanglement are near the boundary. And so what this means in this case is that I'm going to have these 8 contributions that cross the boundary from these entangled particles that are near the boundary that separates A and its complement. So in this case, I have 8 contributions, but more generally, this would be L measured in units of A. So something proportional to L over A is what I would expect at this length scale. But the next thing that I need to do is I need to consider contributions at higher length scales. So what I'm doing here, what I'm trying to represent, is that I would take my theory and I would try to explain it, instead of explaining things with the minimum length scale of A, I now want to explain it on a minimum length scale of 2A. So I'm going to take these 2 by 2 blocks of variables, and I'm going to try to combine them and renormalize them in such a way so that now this is some single variable here. And now you can see that if I consider the entanglement at this length scale, I'm going to have 4 contributions, or more generally, it's going to be L over 2A. And I can continue doing this process at larger and larger length scales. However, once I reach the correlation length of my system, I would no longer expect to have contributions to my entanglement. So we're going to continue with this sum until we reach the point of the correlation length of the system, and then we're going to stop. And you can see that if we're at a critical point, then this correlation length would not limit us, and we would be able to basically continue this sum until we reach the edge of our system or something like that. Okay, so just to make sure you're convinced that this really is an area law in 2 dimensions, I'm just writing it again here. You can see we can just factor out this L over A, and then everything else that we're left here is just going to be some constant number. And even if the case where my correlation length diverges, this sum is still going to converge here. Okay, so I can also consider the case where I have a flat boundary still, as I was talking about in that case, but in higher dimensions. In this case, I still expect something that's called an area law, but it's going to have a different exponent depending on the dimension here. So if I'm in 2 dimensions, then as we saw in the previous slides, we expect the entanglement to scale proportional to L. If I'm in 3 dimensions, we would expect it to be L squared, which is what describes the size of the boundary between these regions. And what I really wanted to emphasize on this slide is the coefficient of this area law. So in this case, the coefficient of my area piece is some coefficient b divided by my microscopic lattice scale to the power of d minus 1. And it turns out that this quantity is non-universal. So this is not something that we're going to be able to use to gain a lot of information about these fixed points. So we're going to need to look a little bit further in the following slides. And the reason I'm saying that this quantity is non-universal is because it depends on this lattice scale. So it depends on this microscopic scale A. Remember we said before that what's so cool about universal numbers is that we could have 2 theories that are very different microscopically, and yet we might be able to find that we have a simple effective theory to describe them with a few parameters. But this theory fundamentally can't depend on these microscopic details of our system. So since this depends on our microscopic length scale, this is definitely a non-universal number. And if we were to renormalize our system in a different way, we would get a different coefficient here. So what we can do now is we can look at more general types of boundaries that we might consider. So in this case, I'm plotting just a more general region A, and we're going to look at specific examples of what we've used for this region. But more generally, if I were to do this and use the same types of arguments on the previous slide, I would still recover the same area law that I saw, but I would get additional predicted corrections to this area law that depend on the size of my boundary, the shape of my boundary, and even the system size. And what's very interesting about doing this procedure is that for a system that's critical, some of these subleading corrections can potentially be universal. So that means they're independent of the lattice that we put them on. They're not going to depend on this microscopic scale A or the overall size of my system L. Okay. So here I'm just talking about some examples of universal numbers that we can extract from different geometries. So first I'm going to talk about what I might see in one spatial dimension, so in 1 + 1 dimension. In this case, the only type of region A I can have is a continuous linear region of length L. And this case has been very well studied and is pretty well understood. We know that the entanglement in this case scales proportional to the logarithm of the length of my boundary. And the coefficient of this logarithm is proportional to a constant that's called the central charge. So this is a universal number that, again, doesn't depend on the microscopic details of my lattice. And there's a lot of studies that have gone into these types of systems in one dimensions, and we understand them very well. We understand a lot of features of these central charges and how they're related to each other at different fixed points. So basically, a major goal of what we're trying to do in this work is do analogous type of work in higher dimensions where these calculations become more complicated. And we have a lot more options for the types of geometries that we can study as well. So in 2 spatial dimensions, here are just some examples of some spatial region geometries that we've studied. So one case we can study is the case where region A is a circle. In this case, we still are going to get that leading linear area law, but we're going to get a constant correction to this area law. And this constant is universal. I haven't written any dependence on a lattice scale A here, so this is some universal constant that we could study. Similarly, I could look at another type of flat boundary where I have two flat boundaries that separate my regions. And I should note that in coming slides, I'm actually going to call this a cylindrical boundary. The reason I'm doing that is because I'm imagining having some kind of periodic boundary condition connecting the left and right sides and the top and bottom sides here. So I'm going to call this a cylindrical entanglement geometry. In this case, I'm also going to get a constant contribution that is subleading to my area law. And another interesting case we can study is where we take a spatial region and we put a region A that has a very sharp corner. In this case, we get a logarithmic correction to our area law with some coefficient. And again, this is a universal correction. Then we can also do this in higher dimensions. So I'm going to talk about some things that we've studied in 3 + 1 dimensions. In this case, if we look at a sphere, we're going to again get a universal logarithmic correction. If we look at the 3-dimensional cylindrical case, we get a constant. It's not going to be the same constant as in 2 + 1. And then if we look at the case where we have a sharp corner in 3 dimensions, we're going to get a correction to our area law that is, again, a universal logarithmic term. Okay, so I'm going to talk about some of these situations in a little bit more detail. So I'll start by talking about some of the work that we did in 2 spatial dimensions. So here I've just kind of rewritten a little bit more clearly something from the previous slide, which is the type of entanglement scaling that we expect when we have a 2-dimensional cylinder. So we expect this leading area law, and then as I said on the previous slide, we expect some constant correction. And it turns out that this constant is actually going to depend on the width of my cylinder. So this is just some ratio that characterizes the width of this region A relative to the overall size of the system. So one thing that ends up being pretty interesting about this type of situation is that there turns out to be a relationship between a cylindrical region and this region that I talked about a couple slides back for the corner. So here again, I have the entanglement scaling for a cylinder, and on the next line, I have the entanglement scaling for a corner, which, as I said, in this case, we expect a logarithmic correction. And in previous work, it was shown in continuum calculations that we expect that if we take the limit where this cylinder becomes really thin, and we take the limit where this corner becomes very sharp, so that this angle is very small, then we know how these universal coefficients are going to behave. And it turns out that they're described by the same universal number kappa. So in this limit, there's actually some kind of a connection between these cylindrical and corner geometries. So a question that I investigated as part of my work was whether this connection occurs at all possible angles and widths that we can study, or whether it's only restricted to this limit, and this limit is the only one that's been able to be studied analytically so far. So I investigated this question numerically, and this is what I found. So the green line here is a result from the literature, from previous work for a 2-dimensional corner. And then in blue are calculations that I did together with my collaborators in this paper. And so we did this specifically for a non-interacting scalar field theory. So what we found is that these two coefficients that are known to be described by the same type of, by the same universal number in the small angle limit are actually quite similar for a larger range of angles, although you can see that the overlap is not exact. And so, as I said, we don't yet have a complete analytical description of why this works, so this is still a question we want to investigate more, of whether this is just a similarity or whether this really is an exact overlap here. Okay, so then I'll just quickly talk about some work that we also did in 3 dimensions. So in this case, what we were mainly focusing on was the case of a trihedral corner. And all that I mean when I say a trihedral corner is a place where 3 flat planes meet. So at this point here. So if I have something like this with these 3 planes meeting, I'm going to expect my entanglement in 3 spatial dimensions to have a leading area law. Then I'm actually going to have a correction that's linear as well. This comes from the edges of my system. And then you can show that due to the corner part here, you're going to have this logarithmic correction. And then I haven't drawn a sphere here, but if you look at a spherical region, you can actually find that you get this leading area law, and then you don't get a linear term, but you just get a logarithmic term after that. So we can see that in both these cases, we get a logarithmic correction in some way. So a question we wanted to investigate was whether it's the same type of universal features that are contained within this v coefficient and this u coefficient. So for the case of the sphere, it's been studied previously for a non-interacting scalar field theory, and it's known how this coefficient behaves as a function of this Renyi index, which again is just an index that describes our Renyi entanglement entropy. So we can consider different values of alpha, and it's just a slightly different measure of entanglement. And so for a non-interacting theory, if I'm talking about this spherical coefficient, we know that this coefficient behaves in this known way. However, there's no such formula available to us for this type of trihedral corner, so this is what we investigated numerically. So we wanted to address 2 questions. The first was whether the coefficient for this trihedral corner would have the same functional form as it does for the sphere. And then if it does, we wanted to investigate whether it has the same overall coefficient. And there was previous work that suggested that there might be a very simple relationship between these coefficients that's just a factor of 1/8. A simple way to think about this argument is if I take a region like this here that kind of looks like a cube, you could imagine that I could deform it into a sphere. However, I would start with 8 corners, and I want to talk about the contribution from just 1 corner. So that's basically where this factor of 8 would come from. So here I'm showing the results of our study. In the upper plot here, I'm investigating whether these 2 coefficients have the same functional form, but I'm not investigating this coefficient, this factor of 1/8 yet, because I've normalized these functions so that they always agree at this Renyi index of 1 here. So similarly to the previous case, I see a lot of significant similarity between these curves, but we're not yet able to be completely confident about whether these curves are actually the same. So what we would like to do is study this type of, these type of quantities in other types of models to see if this type of similarity persists and see if there really is an exact correspondence between these different geometries, or whether they just have kind of similar features, but they're not actually constrained in any way to be related to each other. Then the second question that we did is we tried to estimate that if these curves were, assuming that they are fairly similar, what is the coefficient that describes the relationship between them? And we found that actually this prediction of 1/8 is off both in magnitude and in sign. So we found that the coefficient actually has a different sign, and it's off by a factor of 2.06 in magnitude. Okay, so now I just want to summarize what we've talked about. So if you remember from the beginning, I said that some goals of what we wanted to do was to use universal numbers in order to characterize fixed points of these critical theories here. So we wanted to gain more information about what physics we need to describe these points, these blue points here in this type of plot. So that was one goal. And our second goal was to gain insight into how these different points might be connected or related to each other. So how knowing some universal features of this point are going to tell us maybe some type of information about universal features of these other points and how we can move between them. And I hope that I've convinced you that we've made some progress on this first point. We've looked at a variety of universal features for various types of geometries in various dimensions. And we've noticed that there are some relationships between different geometries that might help us to understand better some of the symmetries of these different points. However, even for this point, we still have a lot of things left to investigate. It would be very interesting to study these types of quantities in more general types of models with more interesting interactions, so more exotic fixed points than what we've studied, and in higher dimensions for different geometries as well. And for the second point as well, we haven't really made much progress into this yet. This is something that is going to be explored coming in the future. So we really want to gain insight into various fixed points, and so far we've just been studying one. So this is a question that I think there's still a lot of exciting work to come out of this type of thing, and so I think you can look forward to seeing more information about universal quantities from these type of features in the future. So thank you.